In the previous video, we looked at exactly-one semantics using idempotent operations. But what if your operations are not idempotent? Like we spoke about the example with running count as one such example. So to generalize how you achieve or how you can look to achieve exactly-one semantics, you can use the concept of transactions. So here the notion of transaction is basically something that gets spread across both the database where you might be storing your results or the Kafka topics themselves, because you could be doing the hot potato principle whereby the output of a data processing is actually going back to one of the other topics in Kafka. And you merge that notion of a transaction with the notion of a transaction that Kafka also provides. And that allows you to reason about correctness more broadly. And that correctness allows you to give a guarantee of exactly once. So what is a transaction? A transaction is basically the database notion of a transaction is basically a atomic operation, meaning that all of the set of changes that are to be done within the block of operations which span the beginning of the transaction all the way to the end of the transaction, all of that happens or none of that happens, right? So that's what atomicity means. So the entire unit of operation is all of that's specified within the transaction block, the begin and end block, and so that entire unit happens or the unit does not happen. So that atomicity property is actually very useful for us to build on top of to achieve exactly-one semantics. Typically, relational databases are the ones which give this kind of guarantee. They provide transaction guarantees as part of database rights. But in this case, with this kind of a complex event processing, architecture, you can actually use all the three layers like Kafka, Spark Streaming with the database to actually achieve this. So first, you have to think about redoing the code of your producer consumer basically to have the notion of a transaction be built in like this. So you begin a transaction, you save the results which are necessary, like for instance the output of whatever you want to do as a result of data processing. Then the offsets are saved, right? You also basically have to make sure that the offsets are basically continuing from where you left off, which means that's monotonically increasing without gaps, and then you commit the transaction. So in this kind of a setup, if there is a failure that happens in between, because the entire transaction block would not have executed, so the unit, which is basically all the things that happen within, would not have executed, and therefore you can actually begin the entire process all the way from the beginning again without having to worry about whether the results are there or the offsets are there, etc. So for instance, if the results are stored in a database and that database is also subject to the same transaction, right? Then you could have that the database abort the transaction because the transaction itself has not committed successfully. Before the commit had happened, there is a failure that happens in between. Likewise for the offsets. So in this kind of a setup, you actually have all of the results and the offsets go lockstep for every single one of the messages. Either all of it happens or none of it happens, and that gives you the guarantee that you can actually restart from where you left off and not have to worry about creating duplicate entries or basically creating duplicate entries or duplicate results. The transaction semantics will give you the exactly-once guarantee that you need. Now, for this to work in practice, if you have two different systems, like one system for results and one system for offsets, then guaranteeing transactions across both is not is actually a very hard challenge. So in practice, this option of using transactions for exactly-one semantics works if you use Kafka itself as both Kafka itself as the destination for results as well as the Kafka for offsets. Then you can use Kafka's producer transaction semantics to actually achieve this seamlessly. But if you have multiple systems that need to be coordinated with, then you have to again go back to the drawing board and figure out what's the best way to convert the operation into an idempotent operation. Okay, so what are the pros and cons of this transaction-based exactly-one semantics guarantee? First and foremost, any kind of transformation works, right? So you could do aggregates, you could do counts, you could do like destructive updates, doesn't matter, because the transaction block is the unit, and therefore if all of the unit succeeds, you're going to get all of it to be succeeding. Or if none of it, if there's a failure in between, then none of it succeeds, which means the restrictive update is rolled back or the aggregate is rolled back, etc. So you'll go back to the same state that was there before that particular aborted transaction ran, right? So that's the biggest advantage. So it generalizes to any operation type. The cons are obviously it's more complex, which means it takes that much more latency, that much more resources from Kafka itself to get this done. Obviously, it requires a transactional data store. In general, like I said, you want both the results and the offsets to be in the same system, like for instance Kafka. That makes the job of guaranteeing the transaction commit and the transaction abort to happen seamlessly. Okay, so with that, we've come to the end of this discussion on Kafka. In the next video, we'll take a look at Spark streaming. So just to summarize, Kafka is one of the most popular options for a persistent store for streaming purposes. So it's a message bus implementation which is circular. It has a lot of optimizations which have been fundamentally thought out from a design perspective, which makes it more conducive for real-time applications. And the design is such that it makes activities like guaranteeing availability, scalability, etc. Super easy and also easy to reason about for a developer. The specifics around semantics is what you have to typically spend a lot of time in terms of getting the design right. And based on the nature of your application, you might or might not desire a certain semantic, right? Like exactly once or at most once or at least once. And there are genuine use cases for all three. But the classic developer behavior, especially if you're not used to big data, is to try to achieve deterministic exactly once. And that's usually costly, right? Because we're talking about a distributed system with multiple, actors involved. But if you still desire exactly once only, there are two ways to achieve it. One, using transactions, which is like a more general purpose. It caters to all kinds of operations that you might do, but it has the practical, limitation that the results and the offsets are all stored in the same system, typically Kafka itself. So it works great for those hot potato kind of sequences that might be there as part of your pipeline, like the intermediate steps in the pipeline. But then when it comes to external results and offsets obviously stored in Kafka, then that kind of a setup, you might have to think about using the other option, which is idempotent operations. So in practice, when you're doing these long pipelines, which have multiple sequences of steps, you use transactions for all these intermediate steps where the results are actually stored back into Kafka again. And then the final step, which is actually going to be writing the data into a database with external side effects, you try to design those operations using idempotency. Yep. Great. So with that, we'll stop with this video.